Hello, and welcome to our site event, where we are going to showcase some of the results from the projects that have been ongoing with the GEO Amazon Web Services Cloud Credits Program. It's a real pleasure to have you join us, and it's also a pleasure to have 5 projects here represented tell us about what they're doing. The way that the session is going to go is we're going to, each of the projects has prepared a video. We're going to watch those, and then we'll take some Q&A at the end. We're going to have a member from Amazon Web Services host this, but apparently she's having connection problems. So I'm going to quickly run through her slides. I have not, I don't know if I'm going to say the right thing, but I will try anyway. So let me share my screen. Okay, can you see it? No? Let's see, I want to show, see this. So here is a brief introduction to the Amazon Web Service and GEO collaboration on Earth observation cloud credits. I'm just going to have to read through these. The Amazon Sustainability Data Initiative significantly reduces the cost, time, and technical barriers associated with analyzing large data sets to generate sustainability insights. Presentation. I have to open another screen, I guess. Oh wait, no, I can do this.
Hello.
Okay.
Oh,
are you back?
Yeah, it kicked me out and then I couldn't get back in the system. I don't know what happened.
Okay. All right. Now. Okay, I think we're almost there, Anna.
So are we in the main session already, or was just us?
Yeah, we're in the main session, and I was trying to go through your presentation, but I failed. So now it's your turn. We're there.
Okay. Well, apologies, everybody. I'm not quite sure what the technical issues were, but glad to be here, and thank you, everybody, for the opportunity to share with you some of the results from this collaboration between AWS and GEO, and more specifically, this program that we put together about now. I guess it was in 2018 that we launched, but I'll tell you more details in a second. Just to give you a little bit of context before we start, we focus on the main part of this session today, which is just to look at the overview and the results from the research done in the last couple of years by 5 of the groups that are part of this program. I would like to give you a little bit of context. So next slide, please. And so this collaboration, I assume you do it, Doug, on your side, or I do it? Okay, perfect. Thank you. So so this collaboration is actually being done under the umbrella of the Amazon Sustainability Data Initiative on the Amazon side, and that's a Tech for Good program that we are running for a few years now. And the goal of this program is really to leverage Amazon's scale and our technology and bring that to the world in a way to hopefully encourage more innovation and problem solving in the space of sustainability. So primarily the focus of this program is on data and make it easier and more accessible for people to use data and make decisions in sustainability space. And specifically, we are going after reducing the costs and the time and the technical barriers associated with dealing with really large data sets. Next slide, please. If you actually can press all of them, it will be easier. Yeah, great. One more. That will be faster. So the premise here is that if we identify what are foundational data sets that are critical for the sustainability conversation, and we make those data sets more accessible and usable by putting them in the cloud next to the services and the tools and the scalable computing, and providing also access to that compute through cloud grants that ASDI provides, that we eventually, or hopefully, will lead to a lot more knowledge creation, innovation, and as we encourage people to share that with each other, hopefully we'll move this space much faster. And so what we are going to see today, next slide, please, is the result of us committing some resources in collaboration with GEO to provide that opportunity for groups around the world. In particular, in this program, we were focusing on developing countries. And the idea here was for AWS and ASTI to bring was up to $1.5 million in cloud credits and services to a collaboration for 3 years. We identified 21 projects in 17 countries. And today, as I mentioned, we are very fortunate to have here with us 5 of those groups to show us some of the work that they've been doing for the last couple of years. Next slide. So this is the list of our speakers today. They'll introduce themselves in a second. And so that you know, we actually pre-recorded their videos to make sure that we didn't have any technical issues. And also because some of them are in other remote areas of the world where it's pretty late now. So we're grateful that they were able to join us. But I will ask Doug, if you don't mind, we'll jump straight into those presentations. And if we happen to have a little bit of time at the end, we'll have a few Q&A with these speakers. But thank you very much. I'll step back and let them speak now.
I'm just plagued with technical issues. Why is this not opening? There we go.
Great.
Okay, can you see it?
Yes.
Sorry, we'll go back to
the though. Yeah. And if those fail, maybe we can put, in this case, Rafael on the spot. And Rafael, do you want to introduce yourself while we try to solve these technical problems? But maybe you can just give us a very high-level overview of the problem. Oh, is it coming now? Can we
okay, we'll just have. Do you hear anything?
No. Rafael, do you mind just introducing your project and maybe address what is the main problem you're trying to solve and where you are in this process, if that's okay?
Yes, of course. Hi, Anna and colleagues and everybody else in this call. In this event, GEO Week 2021. It's a pleasure to be here, and yeah, I can talk a little bit about our project, the Globe that we're developing with support of Amazon Web Services and the GEO Secretariat. Actually, this happens to be the first project that I personally was involved with the GEO and with GEO, and everything started from here. So from there, so I'm very pleased to be able to showcase some results of this collaboration that has enabled us to do lots of things together. We started this project with, well, you can see the slides there, it's good, with the Natural Capital Project from Stanford University to develop this global modeling tool for nature's contributions to people in sustainable development. I work in the Ministry of Environment and Energy of Costa Rica, and we started this collaboration. and we joined the people from the Central Bank of Costa Rica and PRIA's laboratory. We're using the approach that is developed by GEO Bond related to the essential biodiversity variables to use this approach and use Earth observations to understand better the dynamics of ecosystem services in Costa Rica, not using common land use land cover models that may not have, that may use the same characterizations for the different classifications. We were trying to use this approach with the EVVs and a lot of science behind it and a lot of data that comes from remote sensing, but also from other sources of information from like
Rafael, I think we've got it solved now. Should I go ahead and play? Sorry.
Rapid improvements in spatial data and computation present new opportunities for predicting biodiversity at different levels and understanding the relationship between biodiversity and its benefits to people. Our project, a global modeling tool for nature's contributions to people in sustainable development, integrates the essential biodiversity variables derived from Earth observations to improve the accuracy, accessibility, and relevance of ecosystem service modeling. My name is Rafael Monge, and I work as Director of the National Center of Geoenvironmental Information at the Ministry of Environment and Energy of Costa Rica. It's a pleasure for me to be here with you, sharing this presentation about this work. This project is made possible through a collaboration between Stanford University, the Ministry of Environment and Energy of Costa Rica, the Central Bank of Costa Rica, and PRIA's laboratory, with support from NASA's A50 GEO Work Program and the GEO and AWS Cloud Credits Program. The capability of modeling of the fine scale processes underpinning the delivery of ecosystem services at national and global scales has advanced in recent years, with the proliferation of satellite-based Earth observation products at higher spatial and temporal resolution and availability of cloud computing services to make use of it. However, most ecosystem service models and decision support tools are based on categorical representation of land use and land cover, with the assumption that all habitat within each land use land cover type is identical, disregarding heterogeneity in its condition or diversity. We are developing approaches to utilize essential biodiversity variables in ecosystem service models to improve their performance. Or replicable methods use Google Earth Engine and open source software for mapping ecosystem level EVVs like ecosystem function or functional diversity, species level EVVs like diversity of birds and other vertebrates, and other ecosystem services like improved pollination, improved tourism, and improved sediment retention. Or EO-EVV approaches are judged by criteria important for decision making, such as sensitivity, accessibility, and accuracy. Or approaches allow greater sensitivity in reflecting the heterogeneity in ecosystems and attributing different values spatially, not just based on land use land cover type, but ecosystem function or diversity. We'll utilize data that are or can be produced annually, increasing accessibility when compared to land use land cover, which was last updated for Costa Rica in 2012 in a public publication. Finally, major improvements in accuracy are found when comparing our EO-EVV approaches to those utilizing only land use land cover. For EVBs, we derive ecosystem functional types, or EFTs, for Costa Rica using a principal component analysis on phenological air observation data from MODIS and Landsat 8, binding EFTs based on mean, standard deviation, start of growing season, end of growing season, and day of year at maximum and minimum values of the enhanced vegetation index, the start of growing season, and the end of growing season. We then use diversity of EFTs within the flight range of pollinators as an input in our pollination model to set nesting and foraging habitat. Using EFT diversity rather than assigning different values by land use land cover class cuts the overall error in pollinator availability compared to field observation by a third, and reduces underestimation error by nearly 3 times. We developed species distribution models of 463 vertebrates, including 251 bird species, based on climate and land use. We also use advanced EO products, including fractional cover of trees, photosynthetic and non-photosynthetic biomass, using Landsat and other LiDAR and local LiDAR data, paired with over 3 million observations of bird species across the entirety of Costa Rica and 500,000 observations of birds over 20 years and 48 sites situated along gradients. We apply these diversity layers to tourism using social media data, georeference, Flickr, and eBird uploads as proxies for visitation rates. Through spatial regressions and multimodal averaging, we found that tourism is consistently positively correlated with both biodiversity and human-built infrastructure, such as hotels density and distance to roads. Not including biodiversity in the model results in less accurate predictions of visitation that overestimates the value of tourism in easily accessible but less diverse locations. For sediment retention, we also applied an EEVB derived from Earth observations, the EVI, as an indicator of primary productivity and ecosystem function. We tested different vegetation indices and statistics for the use in parameterization of the C factor, which represents the role of vegetation trapping sediment and is otherwise determined categorically by land use land cover type in the universal soil loss equation. We compare model outputs to sediment data obtained from the Costa Rica's electrical agency, ICE, for 49 gauges across the country. The validation showed a vastly superior performance using EVI to set the C factor rather than assigning different values by land use land cover class, cutting the mean square error from 11.5 tons per hectare to 5.8 tons per hectare without any model calibration. Costa Rica is a global leader in sustainability, from reversing or deforestation trends to achieve net forest gains to establishing the first national payments for ecosystem services program to our commitment to complete decarbonization by 2050. Given our track record, our work is not only leading the way in Costa Rica's sustainable development planning, but can serve as an example to the rest of the international community. In addition to the 30+ data products available for national use and now hosted on MINAE's data portal, we have developed replicable approaches and tools that can be applied by technical staff to support reporting on the SDGs and improve biodiversity and ecosystem service monitoring for other policy conventions like the CBD and REDD+, or national accounts. Importantly, It shines a light on how SDGs relate to nature underpinning all the others, which can support more integrative, sustainable development. By moving beyond land use land cover in our methods, we are improving accuracy and enabling understanding of the impacts of improvement and or degradation in ecosystem conditions and how they could affect people. Furthermore, such replicable approaches based on Earth observations can scale up to improve global modeling, making these approaches more accessible to anyone, anywhere in the world. Thanks a lot for your attention. Please follow the conversation using my email or my social media handle at Rafael Monge CR. Thank you very much.
Thank you
I
very
am
much,
Elliot
Rafael.
Christian. I present this project update on behalf of our lead investigator, Jose Mauro of Brazil INMET. Our presentation is also on behalf of our other project partners, AccuWeather, AlertHub.org, Amazon Web Services, UMetNet Meteo Alarm, Facebook, the Global Disaster Alerting Coordination System, Google Public Alerts, the Weather Company, the OASIS Emergency Management Technical Committee, the Open Commons Consortium, USAID, Bureau for Humanitarian Assistance, and the WMO Hong Kong Observatory. Despite today's amazing telecommunications services, there are still too many people in harm's way who do not get timely alerts so they can protect lives and livelihoods. This gap in effective alerting is especially acute in least developed and developing countries, which are often the most vulnerable as well. So this project addresses that gap in public alerting by providing free open source tools enabling the alerting systems of all countries to easily leverage the International Standard Common Alerting Protocol, CAP. One tool, Filtered Alert Hub, supports aggregation of published alerts to simplify access. The link to that tool is given here. The other tool, CAP Editor, provides the means for any official alerting authority to create and publish CAP alerts. The link to that tool is also given here. At project start in 2019, Filtered Alert Hub aggregated about 90 CAP alert feed sources. Today, Filtered Alert Hub aggregates 134 sources. Filtered Alert Hub is operated as the WMO Alert Hub, and a clone of it is operated as the WMO Severe Weather Information Center, or SWIC. It's also being used as the base for the International Federation of Red Cross and Red Crescent Societies, IFRC, Alert Hub. In support of that, the installation process was streamlined and the software was ported from Amazon Web Services to Microsoft Azure Cloud. Now, at project start in 2019, CAP Editor was in operational use by just 3 national alerting authorities. Today, it is the operational system for 22 national alerting authorities. At project start in 2019, that CAP Editor had been initialized across 135 countries for 194 alerting authorities. Today, it is initialized across 201 countries for 354 alerting authorities. This covers nearly all of the national disaster management organizations, as well as the national meteorological or hydrological services. So today, 70% of the world's people live in a country with at least one operational CAP alert feed at national level. This year, 15 international organizations, plus Vint Cerf as an individual, endorsed the Call to Action on Emergency Alerting. That calls for all countries by 2025 to have emergency alerting that leverages CAP. Filtered Alert Hub has opened discussion with other CAP Alert Hub operators such as Google and IFRC about harmonizing policies and practices. The hope is to thereby also increase harmonization among other developers of tools for creating, publishing, or using CAP alerts. Filtered Alert Hub needs better tools for identifying alerts that are defective in ways other than merely their XML validity. For example, CAP alerts often have defective polygons. Self-intersecting polygons seem to result when a publisher simplifies their high-precision polygons for publication without checking those new polygons in detail. We're getting better at detecting for that and alerting the publisher to those errors. But occasionally, we notice valid but inappropriate polygons. So in one case, alerts intended for a place in England, we're getting a polygon placing the alert in the Seychelles. A tool to automatically identify such unreasonable polygons would be very useful. Filtered Alert Hub also needs better tools to monitor system performance against expected service levels. And some of our sources do not remain accessible continuously. So the Filtered Alert Hub itself is built to tolerate that kind of fault, but unreliability at the CAP feed implies local users may be missing out on life-critical alerts. We're working out how to collaborate with the sources to improve awareness of those kind of lapses. We did implement a fix for a problem due to the cross-origin resource sharing policy as implemented on AWS. This was causing a failure to display any CAP alert that included reference to a style sheet being retrieved from a different host. So now the CAP feed references the original URL of the CAP alert rather than the Filtered Alert Hub copy of the CAP alert, but only if that alert specifies a style sheet. Work continues to grow the number of CAP alert sources. Outreach and education of alerting authorities with regard to CAP editor helps with that. For example, we continue working with the UN Disaster Risk Reduction Office to explain CAP to news journalists in television and radio worldwide. We do that through online courseware and by conducting interactive sessions with about 100 countries. And here you see a screenshot and a link to that DRR Media Center. There's also a link to our 40-minute video about CAP for broadcasters. We also organize and run the annual CAP implementation workshop. The last of these, just mid-October, had 750 registered participants. They were from 140 countries, 28 international organizations, and then 68 commercial companies, academic institutions, and other non-government organizations. So the expected impact of this project, that people in harm's way are better enabled to save lives and protect property because countries have enhanced their emergency alerting by leveraging the international standard Common Alerting Protocol.
I'm sorry, I don't know what happened with the end of the video. It looked like Elliot. Do you want to tell us what you were going to say at the very end there?
That was the very end, Doug. At least the way I saw it here. Your
Okay.
communication might be cutting out.
Okay, all right. We'll move on to the next one. Thank you very much.
About our Amazon and GEO project methodology for SDG indicator success. Space Research Institute, NASA of Ukraine and SSA of Ukraine is the main organization in Ukraine within the satellite data usage at country level. Our team was selected for GEO Amazon Cloud Credit Program with the Sustainable Development Goals Assessment project. We work within SDG indicators assessment for several years, and now we are working on opportunity of operational cloud-based service for such kind of indicators assessment. First, we try to implement our experience for the operational use of developed technologies in Amazon's cloud resource. Another collaborator for this project is Institute of Physics and Technology National Technical University of Ukraine, Igor Sikorsky Kyiv Polytechnic Institute, where masters and PhD students are actively involved in projects. The humanity faced with the global environmental problem like global warming, climate change, desertification. All these factors present to the food security and economy well-being for many countries. Here with effective combat with such dangers can be done without efficient strategy, then take into account a measurement of problem state. These measurements named SDG indicators should be monitored for each country in the best way. In our project, we proposed informational technology for 4 SDG indicators assessment and its implementation in the AWS cloud environment based on Open Data Cube technology, with including deep learning algorithm for land cover classification, geophysical modeling, weather modeling, and satellite data analysis, and scaling of this technology for 3 countries, Ukraine, Argentina, and India. By this year, we set up Sentinel-1 data processing workflow in the AWS virtual machines and ingested this data into the Ukrainian data cube. In total, we processed more than 13 terabytes of satellite data for Ukraine. For crop type and land cover classification, optical Landsat 8 and Copernicus Sentinel-2 data were used. For this satellite data, the compositing procedure for specific time series generation has been created. The classification procedures have been created which are based on deep learning approach for land cover mapping, in particular an ensemble of neural network and long short-term memory neural net. To conduct the G11.3.1 calculation for Ukraine, we created the functional urban area layer compliant to the Copernicus Urban Atlas product. Using land cover map for 2016 and 2020 with 10 meter spatial resolution, we calculated built-up area changes for Ukrainian cities, and with use of NASA gridded population of the world product, we obtained this indicator on the city and country scale. The land degradation maps for whole Ukraine for 2016 to 2021 were created based on trend analysis of vegetation indices of Landsat 8 and the Sentinel-2 satellite data in the Ukrainian data feed. The GMS model was used to evaluate crop biophysical parameters. This product is based on the SDG 2.4.1 and 15.3.1 indicators calculation, and in this process, its creation is the most time-consuming task. A striking example in the part of the Emerald Network, nature reserves in eastern Ukraine, within which was deforestation from 2013 to 2021 on an area of 15,000 hectares. Indicator 15.1.1 for 2019-2021 for the regions of Ukraine and for Ukraine as a whole was assessed using the land cover map. The obtained results are validated with available information according to the state statistics of Ukraine. It is planned to improve the existing land cover classification methodology, optimization of algorithms, and scale the technology to other countries, including Argentina and India. In the absence of available land data or in situ data for these countries, we will look with the map of cropland in the country. As a result of the project, we will improve the existing SDG indicators assessment workflow by the use of high spatial resolution data and filling gaps between existing global products and the national ones. As a conclusion, I can say that remote sensing data offer great opportunities for all countries. This kind of information makes it possible to make direct independent analysis for the land, its changes, to track degradation or improvement situation with the land. It is the data of satellite monitoring that make it possible to optimize the work of local authorities, which will be able to obtain the necessary objective information from satellites while in the orbit. This is our work as scientists to separate from the huge flow of information exactly the one that can be useful for public purpose and for the digitalization of the state economy. Thank you very much for your attention.
Ladies and gentlemen, attending at this event, side event of the GEO Week 2021. I am glad to be on this event, and I would like to send my regards to all of you, Dr. Douglas, Crip, and members of the Amazon Web Service. We implemented this project from the credit grant of the GEO Amazon Earth Observation Cloud Credits Program. I would like to present our project that is monitoring dry patchy and flooding in the Lower Mekong Basin based on Earth observation data and Amazon Web Service. I am from Beckwith from the Space Technology Application Center in Ho Chi Minh City, belonging to the Vietnam National Space Center under the Vietnam Academy of Science and Technology. On the behalf of the project team members, I will present a part of the project outcomes on monitoring flooding and dry patchy in the Lower Mekong Basin. The actual study area is part of the Lower Mekong Basin. It is the catchment of the lake named Tonle Sap in Cambodia, downwards to the Mekong Delta, including the lands of Cambodia and Vietnam. This lowland area, the plain is narrow in Cambodia and expanding to be a delta landform in Vietnam. Water supply in this area is from brines and river. Naturally, the plain is annually flooded in rainy season, and flooding normally occurs after July to November or maybe to December, and called as flooding season. At the present, most of the land is for cultivation. Most are paddy rice based on dikes irrigation system, and some areas are intact natural marshes. In this project, we aim at using MODIS and Sentinel-1 data for identifying rice paddy and flooding in the Lower Mekong Basin. Data are used as long as possible and is available. Archive satellite images in Earth observation portals are downloaded and transferred to the instance of Amazon Web Service in Singapore region. A large amount of images of MODIS and Sentinel-1 data is stored, processed, and analyzed, as well as cloud computation based on the service of Amazon Web Service. There are more than 1,800 scenes of MODIS Terra, 8 days composite and spatial resolution of 500 meters are analyzed. There are 46 days data each year from 2001 to 2020, except for 2001, there were only 44 days data. Flooding is identified for either extent and number of yearly inundated days. Usually, flooding in Mekong Delta is called as floating water season. That means the water level rises slowly after water in the Tonle Sap is full, and providing more water to the downstream and runoff downward lower lands. Flooding water brings silt to fields in plain and other narrow resources like fish that support Mekong Delta people in livelihood. From the image of 2001-2020, our observations show that there are slight changes about the spatial extent and duration. These have been raised on some documentation. There has been a decline of flooded area and duration. These are possibly relevant to lowering rainfall on the upstream on local areas and water volume on the stream by new constructed dams, which is still on question. For Sentinel-1 data, which is began in 2015, the amount of available image is less than that of MODIS. Because the satellite acquires image in the Mekong Delta, focusing more on Vietnam part than that does in the Cambodia part. Sentinel-1 images are in level 1 ground range detected. Spatial resolution is 20 meters at post-processing, with about 600 scenes of images. At the present, only images from 2015 to 2020 in part of Mekong Delta have been analyzed for flooding and paddy rise. These images are needed to be analyzed more. For conclusions, we can say that the reason what I have presented are just what we have done by far, and this needs to have adjustment on algorithm and other issues of data analysis. At first steps, we work not fast enough and not as expectation. At the current time, tasks are kept in proper pace, and there have been outcomes as just is been presented. Outcome will be validated and cross-checked to have good result. And most important is, thanks to the policy of the free satellite image, large data from Earth observation portals are accessible via internet to end users without obstruction. And with Amazon Web Service, we are able to work more flexible, and it helps to effectively handle a large data. The last but not the least, once more, I would like to express my great thanks to Dr. Douglas Grip, and I would wish to say directly thanks to many members of the Amazon Web Service who strongly and quickly gave us support when we have troubles while using the Amazon Web Service. And thanks also to my colleagues. We work together to carry out this project step by step. Thank you.
Hi, everyone. My name is Karine. I work at the National Institute for Space Research, INPE, here in Brazil. And I and my colleague Gilberto Queiroz are the leaders of the Brazil Data Cube project here at INPE. And today we will present how we are using the AWS services in the context of this project. So in the Brazil Data Cube project, we are using the AWS services in three main fronts. The first one is to improve the deforestation alerts detection in Brazil. by accessing up-to-date remote sense images from different sensors available on different buckets on AWS. And the second front is to produce multidimensional data cubes for Brazil from big data sets of Sentinel-2 images available on AWS. And the third one is to produce land use and encode information for some regions here in Brazil using machine learning and image time series analysis. And now I will present a little more about these three fronts. Forest Monitor is a WebGIS application used to identify deforestation alerts here in Brazil, based on visual interpretation of remote sense images. This is the graphical interface of the Forest Monitor application. And to increase the Forest Monitor access to different kinds and up-to-date remote sense images stored on AWS, we developed a service called Tile Map Service, or TMS, using the AWS Lambda service to access different kinds of AWS buckets that store Landsat 8, Sentinel-2, and CBERS 4 remote sense images. The architecture of the TMS service is shown in this picture here. And in the Brazil Data Cube project, we are producing analyzed data and multidimensional data cubes for the entire region of Brazil, as you can see here in this picture. And the volume of Sentinel-2 image that you have to process for the entire region of Brazil is around 700 terabytes. And this is a challenge for us. Because of this, we developed an application called DataCube Builder that runs on AWS based on different types of AWS services, such as Lambda, as you can see here, and SQS. The architecture of this DataCube Builder on AWS is shown in this picture, and the graphical interface of the DataCube Builder on AWS is shown in this picture here. And in the Brazil DataCube project, we are using this application, the DataCube Builder application, running on AWS to produce analyzed data in the data cubes of Sentinel-2 images for the entire region of Brazil. Here at INPE, we are also developing an R package called SEEDS that provides a lot of functions to deal with satellite image time series. So this package provides functions to access Earth observation data cubes from different sources, to analyze and improve the quality of land use and land cover samples, to train different kinds of machine learning, deep learning models, and so to classify data cubes, Earth observation data cubes, and to produce land use and land cover maps. And we are using this SEEDS R package running on AWS EC2 service, as you can see here in this picture, to classify image time series extracted from data cubes produced in the Brazil Data Cube project, and to produce land use and land cover information maps from these data cubes. So using the SEEDS R package running on AWS, we are producing land use and land cover maps for different regions here in Brazil, based on this workflow shown in this picture. So we have the data cubes, we extract time series of these from these data cubes. So we use land use and land cover samples to train machine learning, deep learning methods. And so you use these methods and these models to produce land use and land cover maps. This picture shows four different kinds of land use and land cover samples. and their NDVI time series. So here we have a sample that is pasture, and here we can see the NDVI time series of this spatial location that is pasture. Here we have the NDVI time series of a sample that is vegetation, and here we have an NDVI time series of agriculture sample, and here we have an NDVI time series of a water spatial location, a spatial location that is water. And we use these samples and their associated NDVI time series to train these machine learning and deep learning models, and so to produce the land use and land cover maps based on these models and methods. And this picture shows the land use and land cover maps that we produced using this workflow running on AWS. So in this picture, you can see different maps, land use and land cover maps produced in different regions, in different biomes in Brazil. So Caatinga, Pampa, Mata Atlântica, and Cerrado. For Cerrado, we produce a land use and land cover map for the entire biome, because we are working together with the Terra Class team here in Brazil. And these maps can be downloaded and can be visualized in the Brazil Data Cube portal, project portal. As next activities, now we have around $12,000 to use until July of the next year, and we intend to use this credit to complete the Sentinel-2 image data cubes for Brazil, mainly for the years of 2019 and 2020 that we have to complete. And we are producing and storing all these data sets that we are producing here as open data on AWS. As final remarks, so we are producing open data sets that are stored on AWS. These data sets are very useful for researchers that study environmental process here in Brazil using satellite image time series and machine learning methods. And we are also developing useful open source technologies or softwares to create data cubes from satellite images stored on AWS, such as the Data Cube Builder on AWS that I presented here, and to produce land use and land cover maps from these data cubes, such as the seeds are packaged that are presented here. And I think that the big challenge is how to promote or how to fund research with these data sets and technologies on AWS. So thank you very much for the attention and for the opportunity to present our work here. So we can contact us by the Brazil Data Cube Twitter or the Brazil Data Cube website, or by through this email. Thank you a lot.
Thank you so much, Corinne. And thank you also to Raphael and Hannah and Fem and Elliot for your presentations and your work. We don't have much time left, but I was curious, just following up on Corinne's presentation, where at the end she highlighted what they are making available to the community as a result of this project. I'm very curious for the other groups, whether they have plans to share content with the broader public, and if so, what methods or methodologies are they using to do that? Does anyone has any thoughts they want to share?
Just to quickly comment on that, yes, we do want to share. We want to use the official standards in Costa Rica with the National System of Information, and that is connected and also supported with the AWS cloud credits that we're using. So yeah, we're planning to share that for local users, also international users in different platforms, and we're happy to have these cloud credits to do so.
Great, thank you. And Elliot, I know you're sharing your things already broadly, right? Anything else you want to add to that? If somebody is curious about the work you're doing and would like to build on top of it or have access to more details?
Oh, absolutely. Just alert-hub.org. Take a look there. Contact me. We have lots of interest in sharing this thing more broadly, and we're probably going to see more alert hubs coming up as well. Brazil, for example, is offering one for the whole of South America.
Great, thank you. Any other comments or final thoughts before we close the session? Well, if not, I just want to thank everybody for your time again. Doug, did you have anything you wanted to share or ask?
No, I'm
Okay.
apologies again for the technical glitches. This is it's not easy to hold a plenary on completely online, but we got there in the end. So thank you very much. Thank you to all the projects who have done these videos and done such a wonderful job of explaining what they're doing. It's very interesting work.
It is, and thank you very much, Doug, as well, for all your support with running and putting the session together. So thank you all, and yeah, let's keep talking and showing what we've done. This is amazing work, so we appreciate that. Thank you.
Thank you. Yeah, thank you. Bye bye.
Everyone.
Yeah.
Bye bye.
Bye bye.
Bye-bye.